Okay, good afternoon. Lee Sing, Parag, Soplan, Kim Sing. Guys, you're all here, I hope. Kim Sing, can you hear me?
Yes, I can hear you.
Very good, very good. If anything is wrong, let me know because I'm going to turn off my camera. I don't see anybody's face and just talk to the screen. I don't know, okay? So if you have any questions anytime, I can maybe turn it on and also if I just keep my camera off, I can use more space on the screen. Anyway, guys, let's continue. We are going to have two classes today. The first one will be a bit short. The second one will be a bit long. Okay. And we will continue from wherever we stop on next Tuesday. Okay. So, participants, mute all. Yes. All right. So we started this, what is it, chapter with the definition of matrix, right? And after that, matrix operation, that is addition, subtraction, or multiplying two matrices. And after the matrix algebra, some algebraic properties of matrices. And in our last class, we talked about the inverse of a matrix, right? Any matrix, if you're given n by n square matrix, and if it has inverse or it is invertible, how did you find this? We use what is it? Again, Gauss elimination method or simply Gauss method, right? So we need to form our super augmented matrix and at the same time, by just applying the same bunch of elementary operations, when we actually transform A into identity matrix, on the right-hand side, we actually have new matrix, right? Simply, we are transforming I into new matrix. That new matrix will be the inverse of the matrix, if it has. But sometimes, you know, when you're performing these elementary operations, if you actually if you see any zero row, immediately we can stop. That means that that is not invertible. Okay. So, and also after that, actually, if you remember, we did one or two examples, right? How to write a given matrix as a product of elementary matrices. Okay, so now in our class today, we are going to talk about the special one, the special factorization. We call this the LU factorization because, you know, of course, you can factorize every number, right? Or a lot of numbers. But among this factorization, I don't know how much you remember, but in from grade 7, right? And the most important one is the prime factorization. For example, prime factorization means that writing a number as a product of prime numbers. Okay, so like for example, 12, right? This 12, for example, I can write it as 2 times 2 times 3. Each number is prime number. And this kind of factorization is really important. Of course, in different ways, we can factorize it as maybe 2 times 6, or you can factorize it as 3 times 4. But among these factorizations, this one is the most important. Why? Because every number, every factor here it is a prime number. Okay. And also for matrices, this LU factorization is more important than other factorization. Now we are going to talk about this. Now, if you look at these matrices, the first one is 3, -1, and 9, -5, right? So see here, I can just factorize this. A bit later, we'll talk about how can I do that. So 1, 0, 3, 3, and the 3, -1, 0, -2. And whatever it is here, if I just label this by A, and I'm going to label this matrix by L, and this one is by U. Why is this so? Because if you look at this matrix, if I just draw the diagonal, above the main diagonal, all the elements are 0. And along the main diagonal, all elements are 1, right? And the second one, it's upper. Why? Because if you draw again diagonal, below the diagonal, all the elements are zeros. Actually, we have only one here. So that's why we are going to name this as upper triangular matrix. The first one is lower unit triangular matrix. Why am I saying unit? Because all the entries in the main diagonal, they are 1. Another example, for example, let's say 2, 3, 1, 5, right? This one is, let's say A, it is 4 by 4 matrix, right? So also by performing some elementary row operations, I can reduce this to, for example, this form, right? On the right-hand side. Again, let me just label this by, what is it? And maybe I can just write this L times U. Why L times U? The first one, if you just draw the main diagonal, all the entries above the main diagonal, they are zeros, right? This one is 0, 0, 0, 0, 0, 0. And how about the second one? All the entries below the main diagonal, they are also zeros. But in our L in this book, actually, all the entries in the main diagonal, they are ones, okay? So factorizing a given matrix in this form is called LU factorization. And also it is a kind of, what is it, built-in function. Okay, for example, if you just write in the Google search LU factorization online calculator, and you can just use that calculator to factorize a given matrix. Okay, now if you consider this example, 2, 1, okay, 2, 1, 3, just a second. I need to 2, 1, 3, 4, negative 1, 3, 1, right? So now, how am I going to do this? By performing a few elementary row operations, right? Actually, we can reduce this to, what is it, row echelon form. Or, I don't know, I can just create zeros under this main diagonals. How do I do that? The first one is here. The first one is I can multiply the first row by -2 and add it to the first row, right? And those operations, let me just write here. Our first operation is, what is it? R2 minus 2 times R1. And the second one is I can just add the first row to the third row. So here we have R3 plus R1. Now, if you perform these two operations here we have 2, 1, and 3. -2 plus 4 is equal to 0. And -2 plus -1, that's equal to -3. And what is it? -6 plus, what is it? -6 plus 3, that is equal to -3. And if you just add the first row to the third row, 2 plus -2, that's equal to 0. 1 plus 5, that's equal to 6. And 3 plus 5, that's equal to, what is it? 1 plus 5 and 3 plus 5, that's equal to 8. Okay. So what is the next thing? If I just multiply the second row by 2, right, add it to the third row, again, we can create zeros here. The third one is, what is it? R3, right? And plus 2 times R2. So here we have, actually not arrow pads, here we have 2, 1, 3, and 0 minus 3 minus 3. And here we have -6 plus 6, 0. -6 plus 8 is equal to 2, right? And you see here now, all the entries below the main diagonal, they are zeros. So actually, we have just created or obtained our U, upper triangle matrix, right? So what did I do here, right? If I just, again, label the first one by E1, that's the first elementary row operation. This one is the second elementary row operation. And this one is the third elementary row operation, right? So now this new matrix U, right? This U is equal to, here we have E3 and E2 and E1, and here we have 8, right? So I actually perform the first one, right? We know that actually this elementary matrix, right, and elementary operation, they have the same effect on the matrices. So if you just actually perform these 3 elementary operations on A, we obtain U, right? Now from here, how can I take this B3, B2, E3, E2, E1 to the right-hand side? I should multiply both sides by the inverse of this, right? So at the time, this A will be equal to, here we have E3 and E2 and E1 inverse, and here we have U, or that's equal to E1 inverse and E2 inverse and E3 inverse, and here we have U, right? So now actually if we just find this one, this gives us our L. And do you know how to find this, what is it, inverses of, what is it, E1 and E2 and E3, right? And what is the inverse of E1, for example? And just I need more space. Let me just write the top. Okay, it's just an example, actually, introduction. And I'm going to write this at the top here. So what is E1 inverse? E1 inverse is equal to, what is it? Multiply the first row by -2 and add it to the second row. So that is this one, right? 1, 0, 0. And so here we have -2, 1, 0, 0, 0, 1. And how about the second one? Let me just, okay. And the second one, E2 inverse, right? Just add the first row to the third row. So the first row is 1, 0, 0, 0, 1, 0. And here we have 1, 0, 1. That's our E2. And how about E3? E3 is multiply the second row by 2 and add it to the third row. So here we have 1, 0, 0, 0, 1, 0. Multiply the second row by 2. So it is 0 and 2 and 1. So these are the inverses of these three elementary matrices. Now, if you just multiply them, what do we get here? This L, let me just write here, this L will be, if you just multiply them each other, this L will be, what? It will be 1, 0, 0. I'm sure that all upper part is 0. Here we have 2, 1. And also here we have -1, -2, 0, and 1. Okay. Now from here, actually 2, 1, right? Actually 2, 1. Later we will see this 2 and 1. As see here, we have 2 here, right? And that is 2 here. And how about 3, 1 and 3, 1? Here we have minus 1, and that's why here we have -1. And how about his 3, 2? Here we have minus 2, and that's what 3, 2 and 3 is -3 actually. And also in a very shortcut, you can get this very quickly, okay? And just here, the idea about how we factorize or find the LD factorization of matrix A. So now the definition, unit lower triangular matrix. Okay, what is a unit lower triangular matrix? It's a matrix, okay, where all the elements in the main diagonal, they are ones, and elements above the main diagonal, they are zeros. Okay, such matrices are called unit lower triangular matrix. And how about upper triangular matrix? Here, I'm not using these units. So that is U, and all the entries in the main diagonal. Also here, we don't have any condition here for lower triangle matrix. It must be 1, but for this, it doesn't matter. But here the condition is all the entries below the main diagonal, it must be 0. Such matrices are called, what is it, upper triangle matrix. And what is good thing here is, just later we'll just maybe give this as a small theorem. If you multiply 2, let's say L1 and L2, lower triangular matrices, and also the result will be lower triangular matrix. And also if you multiply 2 upper triangular matrices, and also their product will be upper triangular matrices. Okay, you can just check this as an example, or proof is a bit not long, but you need to a bit do some brainstorming. That's why I'm going to see this at least now. Maybe in the class, if you are interested, we can do this. Again, in our example, let's see here, this 2, 1, 2, 3, 1, 5, this 4 by 4 matrix, right? That's A. It is actually expressed as a product of these two matrices. This one is, what is it? It is L and times U. That's called LU factorization of matrix A. So find the LU factorization of the given matrices. Okay, so again, if you're given two matrices, now I'm just going to do this in very, very simple way. Okay, what is it? So that simple way is if you are performing, let's say here we have Ri, okay, minus, and here we have K times Rj, okay. So in new matrix, that's what is it? It is, what is it? It is lower triangle matrix, right? It is, what is it? Lower triangle matrix in a way. So this will be lower, this L of Ij will be equal to just this K. Okay, now you will see this in this example. So let's start with A, for example, part A. So this A is equal to, here we have 2 and 1 and 1. Here we have 4 and 3 and 3. And here we have 8 and 7 and 9. Okay, so the first operation is, let me just write them here. The first one is, again, what is it? R2 minus 2 times R1, right? So that is, what is it? 2, 1, 1. Multiply the first row by -2 and add it to the second row. -4 plus 4, that's equal to 0. -2 plus 3, that's equal to 1. -2 plus 3, that's equal to 1. And here we have R3, what is it? Minus 4 times R1, right? If you multiply the first row by, what is it? -4 and add it to the third row, so we can create 0 under this 2. So -8 plus 8, that's equal to 0. And -4 plus 7, that's equal to 3. -4 plus 9, that's equal to 5. Okay, now we have created zeros. And one more thing is, what is it? I should multiply the second row by -3, right? And add it to the third row, right? So here we have, what is it then? Here we have 2, 1, 1, and 0, 1, 1. And here we have 0, -3 plus 3, -3 plus 5 is equal to 2. So this one is upper triangular matrix. Then this A will be equal to, here we have lower triangular matrix, right? And times upper triangular matrix. That is 2, 1, 1, 0, 1, 1, 0, 0, 2. Okay. And how about this one? We know that this will be 1, 0, 0, also 1 and 0. This will be 1, right? How about these entries? How do I write this? Again, by this, right? What is ij entry? So here we have L 2, 1. But be careful here that it must be minus here. So here we have 2, right? So it's 2, 1, it will be 2 here. And maybe I can just write this in different color. So this one is 2. And how about 3 and 1? The 3, 1 is 4. So this one will be 4. And how about 3 and 2? The 3 to element, that is 3. Okay, so that's our workout. If you just factorize this, you will get, what is it? Matrix A. So definition. Now let's just formalize what we have just done. Let capital A be square matrix. A factorization of A as A equals L times U, where L is unit lower triangular and U is upper triangular, is called an LU factorization of A. Okay, that is how we define the LU factorization of matrix A. If A is theorem 3.15, if capital A is a square matrix that can be reduced to row echelon form without using any row interchange. That is a condition here. Here we have, what is it? Without using any row interchange, then A has an LU factorization. Okay, if you can reduce the given matrix to reduce row echelon form, right? Reduce row echelon form, reduced to row echelon form without using any row echelon interchange, then always it has, what is it? LU factorization. For example, not example, we are going to say one example how we use this LU factorization to solve system of equations. Just another method, okay? So because by using Gauss elimination method, we can solve this, right? And now we are just going to make use of this LU factorization to solve this system. So using the LU factorization of A, solve AX equals B. All right. So what are we going to do here is suppose that this A has LU factorization. If A has LU factorization, right? So that means that I can write A as L times U. So now if I substitute into this equation instead of A, here we have AX that's equal to B, right? What is A? I can write LUX that's equal to B. Okay, so now if I just label this, like for example, L, here we have UX, right? That's equal to B. So if I just label this ux by y, let's say y is equal to ux, actually they are vectors. What we have here, here we have L times y is equal to b, right? And what is L times y? L is just lower triangular matrix, right? So by forward substitution, from here I can find y. Now, if I just substitute this into this equation, right? And by back substitution, we can find u. Okay, we are just going to use this method. So to do this one in our first step, we need to find the LU factorization of A. So how do we get this? Again, here we have A that's equal to 2, 1, 3, and 4, negative 1, 3, negative 2, and 5, and 5, right? So the first step, again, actually, let me just open maybe here. All right, I'm going to do my operations here. What is it? The first one is R2 minus 2 times R1. That's the first thing. So here we have 2, 1, 3, and multiply by negative 2, the first row, added to the second row. So here we have 0, negative 2 plus negative 1, that's equal to negative 3. And here we have negative 6 plus 3, that's equal to negative 3. Actually, I think we have already seen this anyway. You can just do this one more time. And the second one is add the first row to the third row, right? If you just add this, 2 plus negative 2, 0, 1 plus 5 is 6, 3 plus 5, that's equal to 8, right? And the next one is, actually, it should be like this. So 2, 1, 3. The next thing is R3 plus 2 times R2. So 2, 1, 3. Let's do close. 2, 1, and the 3. Here we have 0 minus 3 minus 3, and 0 minus 6 plus 6, that's 0, minus 6 plus 8, that's equal to 2. Okay. So now using this one, we can just write the LU factorization of A, right? What is it? A is equal to LU factorization. Let me just write here L times U. What is its L? So it is 1, 0, 0, 1, 0, right? And here we have 2, 1. What is 2, 1? And 2, 1, that's equal to 2. So here we have 2. And how about 3 and 1, right? Here we have minus 1. So it must be negative 1. And how about 3 and 2? It is minus 2. So it must be minus 2. And here we have 1. And how about U? U is 2, 1, 3, and 0, minus 3, minus 3, and 0, 0, 2. Okay, that's how we, what is this? Find the LD factorization of A. In our next step, okay, now we are going to label this one. Actually, this UX, right? L times UY is equal to B, because in our case, Y is equal to U times X, right? So if it is so, then L times Y is equal to B. So we are going to solve this equation. What is L? If we just write this L, L is, here we have 1, 0, 0, 2, 1, 0, minus 1, minus 2, 0. Sorry, it is 1. And Y. Y is, here we have Y1 and Y2, Y3. On the right hand side, we have B. What is B? It is 2 and 7 and 11, right? So now if you just write the corresponding matrix for this, what do we get here? You see here, Y1, right? In the first one, we're just using forward substitution. Y1 is equal to 2. In the second one, 2 times Y1, 2 times Y1 plus Y2, that's equal to 7. And the third one is negative 2y1 minus 2y2 plus y3, that's equal to 11. By forward substitution, we can find what is it? And y1, y2, and y3. So from here, y is equal to, what is y1? That's equal to 2. And how about y2? 7 minus 4, that's equal to 3. And how about y3? Minus 2 minus 8 is plus 2 times y1 plus y2. y1 plus y2 is 5, right? And 2 times 5 is 10. So 11 plus 10. So that's equal to 21. So that is 2 and 3. And what is it? 2, 3, and 11. Okay. Two is 4. Okay, let me check. Minus 1. All right, so this will be Okay, this one, right? It is 2, and this should be just minus 1, minus y1. All right. So there's 1, 0, 0, 2, 1, 0, minus 1, minus 2, 1, right? So that's equal to, okay. So from here, 2, it is 7 minus 4, it is 3, and it is minus 1. So 11 plus y1, it is 13. 13 plus 6, it is 19. It's 19, right? Okay. 2 and 3 and 19. Okay, that's the first part. This I need another slides. Unfortunately, couldn't fit here. Okay, so let me just keep in mind 2, 3, 19. So y is equal to 2 and 3 and 19, right? So we're talking about this thing, right? L times y is equal to b. And what is y? Y is equal to u times x. So now we know u. So now I'm going to write this equation to find x, because in our equation we need to find x. So what is u? U is 2, 1, 3. So u is 2, 1, and 3. It should be 0, and this is 0, and also this is 0, right? So minus 3, minus 3, 2. So this one is minus 3, and this one is 2. Times x. So x is, here we have x1, and x2, and x3, right? So that thing is equal to y. What is y? Y is equal to 2, and 3, and 19. Okay, so now in back substitution, we can actually find what is it, x1, x2, x3. So from here, what we have here, from the last one, right, 2 times x3, that's equal to 19. Now from here, x3 is equal to 19 over 2. And if you substitute the second one, minus 3 x2 minus 3 x3, that's equal to 3. Divide both sides by minus 3. So x2 plus x3, that's equal to minus 1. So what is x3? Take x2 to the right-hand side. Actually, we need to find x2, right? x2, it is minus 1 minus x3, that's equal 19 over 2. So that is minus 21 over 2. And the first one, so here we have 2 times x1 minus x plus x2. So x2 is, let me just write here as, what is it? It is 2 minus x2 minus 3x3, right? So that's equal to 2 minus x2 is plus 21 over 2. And the x3 minus, it is 57 over 2. So that's equal to 2. 4, 25, 25 minus 57, it is minus 32, right? So from here, x1 is equal to minus 32 over 4. So now, dot, dot, dot. So the solution of the system, that is x1, x2, and x3, is equal to, what is it? Minus 32 over 4, that is minus 8. And the second one is minus 21 over 2, 21 over 2, and 19 over 2. All right, so we have time. 3.16, theorem 3.16. If A is an invertible matrix that has an LU factorization, then LU is unique. That means that actually there's only one LU factorization of A. If it has invertible, and what is it? It has LU factorization. Why is it so? Actually, proof is, I just want to prove again, mathematical way. Mathematical way means a pure mathematical way. Usually, how do you prove that? we suppose that, okay, since we are going to prove that it's unique, it's only one. Now just actually think the opposite, okay? Suppose that it has more than one. Let's say this two. So the first one is, let's say, I can write it as L times U. And also we have another one where here we have L1 and the U1, okay? And so we are assuming that it has two different LU factorization. A is invertible and it has LU factorization, but we have more than one. Now we are going to prove that actually this L is the same as L1 and also U is the same as U1, right? How do we do that? How do we prove that? Now, here, since actually this LU equals A, L1 and U1 is equal to A, that means that this LU, it must be equal to L1 U1. All right. So now if I just multiply both sides by some matrices, I'm going to multiply by L1 inverse, LU, on from the right hand side, U inverse. That's the same thing. Here we have L1 inverse. On the right hand side, we have L1 U1 and also multiplies by, what is it, U inverse. So here we have U inverse. Okay. So here, of course, actually this L1 is invertible because lower triangle matrices, they are invertible, right? Because, what is it? Because A is invertible and its reduced to echelon form is an identity matrix I, right? So what is L1 inverse L? That's equal to I. So here we have U, sorry, they are not the same thing. We don't know yet, right? So that is L1 inverse L. And how about U inverse? That's equal to just I. On the right-hand side, L1 inverse L, that's equal to I. And here we have U1, U inverse. So this I, right, just identity elements, it gives us this equation. On the right-hand side, U1 and U inverse. On the right-hand side, we have lower triangular matrix, right? There's something, what is it? Like this. All the entries everywhere else, it is zero. On the right-hand side, we have something like this, right? All entries below this, it is zero, right? And we are claiming that these two things are equal. When two things are equal, if all of these entries here, they are zeros, otherwise they're not equal to each other, right? And also entries on the main diagonal, they must be the same, right? Which one is it? That means that the only matrix it has this property is that is identity matrix, right? All the entries in the main diagonal, they are ones, above it is zeros, below it is zeros. That's why it is unique. Okay. Now another, what is this? PTLV factorization. Guys, if I start now, I think, can we finish this in 15 minutes? Okay. All right. I think so we have time, 5-6 minutes. We now explore the problem of adapting the LU factorization to handle cases where row interchanges are necessary during Gaussian elimination. In the previous ones, actually, we didn't have to actually, what is it, interchange any two rows, right, to reduce the given matrix into, what is it, row echelon form. But how about in this case, for example, if we just perform the first one, what is it? The first one is R2 minus 3 times R1, right? So here we have 1 and 2, -1, multiplied by -3, it is 0, -3, it is 0, and -3 is 3 plus 2, it is 5. And add the first row to the third row, 1 minus 1, 0, 2 plus 1, it is 3, and -1 plus 4, it is 3, right? How can you continue this? Because now it's already zeros, right? I cannot actually create 0 here because above the 3, it is 0. So now by actually performing something new, we actually, if I just interchange, right, these two rows, right, if I just interchange these two rows, everything will be fine, okay? And suppose that if I just actually multiply this A by elementary matrix, okay, A, by I will interchange this. At the time it becomes, what is it? Here we have 1 and 2 minus 1. So it will be -1, 1 and 4, and 3, 6, 2, right? So how can I just interchange this? And what is this matrix? If you remember, how can I do that? I'm just interchanging the second and third row. So it is 1, 0, 0, This will be 0, 0, 1, 0, 1, 0, right? So now I can just reduce this to reduced row echelon form. Now, if you perform the first one, so here we have, let's say, the first one now, it is R2 plus R1, right? So that is 1, 2 minus 1. It is 0 and 3 and 3. And R3 minus 3, R1. So that's equal to minus 3 plus 3, 0. Minus 6 plus 6, it is 0. And 3 plus 2, it is 5, right? So it's already LU factorization form. So that means that now here we have E times A equals L times U, right? Here we have L times U. And now, how can I actually take this one to the right-hand side? If you multiply both sides from left, right, by the inverse of E, so we will have, what is it? E inverse and LU. Now, if you remember, actually, this elementary matrix is type 2 or type 1, actually doesn't matter, right? How did I form this elementary matrix? By just interchanging two rows, right? Interchanging two rows, also its inverse is the same. So that's just equal to E, L, U. Sometimes we may have to actually do not only one, maybe more than one or two or three row swapping operations, okay? At the time, we will have something like this, maybe after, what is it, E2, and maybe, let's say if it is 2, E2, E1, then we can reduce this to LU factorization, right? So now we are just going to give a special name to this. Right? So permutation of a set of objects, all right? So a permutation from math, what is it? It's a set of distinct objects, is an arrangement of the objects in a specific order without repetition. Right? For example, you know that if you're given 3 letters, right, A, B, C, in how many different ways we can permute, we can arrange this 6 different ways, right? It is A, B, C, A, C, B, B, A, C, B, C, A, or C, A, B, C, B, A. That's the definition of permutation. But what is permutation matrix here? The permutation matrix is a matrix obtained by permuting the rows of an m by n identity matrix according to some permutation of the numbers 1 to n. Every row and column therefore contains precisely a single one with zeros everywhere else. So actually, if you just obtain new matrix, maybe you're given, let's say, 4 by 4 matrix. I change the first one with the second one and third one with the fourth one, right? So that new matrix is called permutation matrix. So these are the examples. Let's say this one is, we just interchange the first and the second rows, permutation matrix. How about here? Third row with the, and the third row is in the first row, right? And the first row in the second row, and the second row is in the third row. That's also an example for permutation matrix. How about in the last one? And matrix C, right, the third one, actually the second row in the first row, and the last row in the second row, first row in the third row, and the third row is in the fourth. We're just interchanging the rows of the identity matrix. So the new matrix is called permutation matrix. Consider the matrix A, where it is 1, 2, minus 1, and 3, 6, 2, sorry, and what is it? Negative 1, 1, 4. Guys, only 51. Okay. Unfortunately, I couldn't finish. Anyway, let's pause here. Okay, 15-minute break. After that, we will continue from here.